Okay, well, good morning, everybody, and welcome to the second day of the OpenMM workshop. This morning I'll be talking about how you create and customize force fields in OpenMM. It will be more of a laid-back presentation, not quite as a fast-paced as the one yesterday. And there will be a short exercise included in this, so I'll go through some of the slides really slowly and make sure everybody is caught up with the steps of the exercise. So to repeat a few things that I said yesterday, there's a really wide range of simulation domains which are appropriate for different applications, and OpenMM is really well adapted to performing, say, atomistic molecular mechanics simulations, although its capabilities do extend somewhat into the coarse-grained domain. And when you run molecular mechanics simulations, the interactions between atoms and molecules is described using a model, using an empirical model that's called a force field. Okay. Force fields kind of represent our physical intuition of what molecular interactions should look like. Like, for example, a small vibration in a chemical bond about the minimum should be describable using harmonic potential, and same with angle vibrations, like on the lower left. And dihedral angles, you should be able to represent that using some kind of periodic potential. And the molecular motions and the energies that they go through might look something like this. And then if you have two atoms that are not bonded together, they might have an attractive or repulsive interaction at long range, but it's always going to be repulsive at short range. So the interaction between a sodium ion and a chloride ion might look something like this. They attract each other, and then they come into the repulsive region and they bounce back. Your simulation accuracy, of course, is going to depend critically on your choice of parameters. And in fact, the challenge in choosing parameters for your molecular mechanics simulation is going to depend very much on the system that you're studying. So there are certain types of systems that can be considered common in molecular mechanics simulations, and those are usually proteins and water, okay, and some of their associated molecules, like ions, because they are required to maintain charge neutrality. In protein simulations, ions are also quite common. Things like things like carbohydrates and lipids are a little bit less common, but there do exist published parameter sets for those. So these force fields, you might recognize some of these like by the names amber or charm, and they ship with OpenMM and most MD codes. So if the system that you're simulating is entirely encompassed by like proteins and water, well, your main challenge is choosing which force field is most appropriate, right? Like there's going to be like 50 of these or hundreds, and you just have to browse through the literature and see which one is best for your application. Now molecules. So general organic molecules can span a much wider range of chemical space than biomolecules. Okay, and for these, like say for a molecule like vancomycin showed in the middle, it's an antibiotic. Okay, there may or may not be a force field for this molecule that is published in the literature, and certainly there isn't a force field for vancomycin that ships with OpenMM and probably any other MD code that I know about. So if you want to say do a simulation of vancomycin, actually killing a bacteria or something, the way to obtain parameters for this molecule are to go through what are called general force fields. So general force fields are not they are not so much like pre-existing force fields for every conceivable molecule. It's more of a procedure for generating a force field for a very wide range of molecules. Okay, so something like GAF, the generalized amber force field, or CGen-FF, the charm general force field, those are procedures that are relatively easy to follow, where you can, where if you follow the procedure, you get a parameter set that you can then use in your simulation that should be consistent with the rest of the Amber force field or the rest of the charm force field. But hopefully you're not relying on it too much, because the parameters might not be very accurate. Finally, you have molecules that could be that could be very rare and extremely difficult to simulate in molecular mechanics. For instance, if you have inorganic molecules containing metals, the picture on the right is the oxygen evolving complex in photosystem 2. Any force field involving transition metals is going to be very rare. There are small numbers of transition metal systems where parameters have been published in the literature, but they probably only deal with small vibrations of a static geometry rather than large-scale geometric arrangements, and definitely no chemical reactions. So if you have something like that in your simulation and you expect it to undergo a chemical reaction, your best choice is probably to use a method like OpenMM, where you treat most of your system using classical molecular mechanics, but you carve out that little part that's undergoing the complex transformation and use quantum mechanics on it. But otherwise, you might have to consult the literature and see what functional forms they've published and see what parameters they've come up with to get a good set of parameters. Okay, so here's where you might be getting the force fields from, and the rest of this talk is going to help you become familiar with how to implement a force field into OpenMM. Okay, so the overview of the exercise is going to be like this. I've provided a bunch of geometries where a water molecule is interacting with a formaldehyde molecule. Okay, the formaldehyde molecule is actually like the force field for formaldehyde doesn't automatically ship with OpenMM. So I'll walk you through a force field XML file for formaldehyde. It's one of the simpler molecules, so the force field file does fit on the screen. And where yesterday you might have been running a lot of molecular dynamic simulations, in this exercise we're just going to be doing a potential energy scan, where we're going to loop through the set of geometries that I've already provided for you, and I got all of these geometries using some kind of a quantum geometry optimization. And so all of these are PDB files that are already in your exercise directory in the movie. And they represent minimum energy geometries where the angle that's highlighted, highlighted using the yellow dotted line, is fixed at a different number. So you see, as I scan through this, the hydrogen, oxygen, carbon angle that's highlighted using the yellow dotted line is being varied from 60 degrees to almost 300 degrees. And when you calculate all of these energies using a high-level quantum method, which by certain standards, maybe that should be our reference, that would be the black curve on the lower left. If you calculate the same energies using the OPLS-AA force field, which is one of these somewhat general force fields for organic liquids, you get the red line, and you can see that it looks qualitatively incorrect. And if you use the higher accuracy amoeba force field, which is implemented in OpenMM but not a part of this morning's exercise, you get something that looks a little bit more like the quantum result. And an interesting aspect of this is we can actually reproduce a literature figure, which is shown on the right. They've done the same calculation using the three force fields. Well, the first one's the quantum method, the second one OPLS, and the third one is amoeba. But one important difference between the two figures is that theirs is symmetric while ours is not. And in fact, the reason why theirs is symmetric is because they just calculated the left half and reflected it across the middle. So it's interesting that we also kind of reveal this hidden asymmetry that was in the that was not shown in the original literature figure. Okay. So now we're going to start getting into the kind of the technical aspects of OpenMM, and let's familiarize ourselves again with the main components. Okay. So for those of you who might have become familiar with other MD codes, it might have been a bit of a puzzle to see that there is no single executable that's called OpenMM. In other MD codes, there's usually a single executable that will run your molecular dynamics simulation for you, like Sander, PME-MD, Charm, MD Run. I can name a bunch of these. In OpenMM, we currently don't really have this, right? Rather you write a Python script that runs your simulation for you. And the important components that you might want to include in your Python script are all in this complicated looking diagram here. It actually took me a while to lay out the concepts in this diagram. And basically, you always want to get to the simulation object, right? Once you have the simulation object, you can then run your simulation. Well, you do need to set the positions before running the simulation, but basically your goal is to get there. And all of these, every little symbol is a class that is available to you in your Python script. The diamonds are API layer classes, meaning they're written in C++, and an interface to your Python script is automatically generated, whereas anything that's a circle is an app layer class, meaning that's actually written in Python. That's not so important from a user perspective. And you can see that in order to get to the simulation object, there's several ways in. Okay, and what we really learned about yesterday morning is you can start with a PDB file. The PDB file contains the positions of the atoms and also contains information about how the atoms are connected together. And you can, and if you have a PDB file and a force field file, which is the specification of the interactions and parameters that OpenMM recognizes, you can combine the force field object with the topology in the PDB to create the system. Okay. There are other ways to create the system, like you can take an Amber parm-top file and create the system directly from there, in which case you don't need the force field XML file anymore. Also, the system can be written to disk in a self-contained system XML file using the serializer. I'm also going to be talking about that. And the input coordinate file, the arrow is kind of missing from this, but it allows. You see, the Amber input coordinate file doesn't contain the topology; it only contains the positions. But because the parm-top file is all you need to create the entire system, the combination of these two files also allows you to create the simulation object and run your simulation. Okay, so are there any questions about this? Yeah?
I was wondering, from yesterday, where do the velocities of the molecules come from?
That's a great question. So you get to set the velocities in your Python script, right? But then, but there's a certain standard when it comes to what velocity you should give your molecules in the simulation. So one way to do it is you don't set the velocities at all, and they start off at 0. And then your molecules would then just start to accelerate based on their initial positions. But if you put a thermostat in there, say if you use the Langevin integrator or the Anderson thermostat, and you set it at some temperature, then the velocities of the atoms will eventually reflect the kinetic energy in the thermostat after like a few picoseconds, and then you can gradually heat the system up until you reach room temperature. And another way to do it is to take the velocities from a Maxwell-Boltzmann distribution. Okay. I'm not actually sure if there's a if there's a function in the OpenMM library that automatically makes those for you. I just have a function to make it myself. Peter, do you know? Like, is there a Maxwell-Boltzmann velocity generator? Okay, there is. Okay, yeah.
Context class, it's like set velocities to temperature.
Okay, got it. Yeah. So there's So within this context class, because classes have methods, they're all functions that belong to the class. There's a method that generates the velocities there. So if I knew that, I could have made the answer a lot faster. Mm-hmm. Okay, any more questions? Okay, so let's talk about the OpenMM XML force field format. So OpenMM describes its force fields using the XML format, and one of the section that I've decided to introduce first is the residue template section. Okay, so if I want a force field for formaldehyde, and OpenMM does not natively recognize a molecule like formaldehyde, I need to I basically need to specify a template for formaldehyde so that when I read the PDB file, it will automatically recognize which atoms belong to formaldehyde molecules and which atoms belong to other molecules. And you can see that I've highlighted the various types of the residue section in different colors. The residue has a name. The name is actually not used, but to avoid confusion, it's good to set the residue name to the same as what you're going to use in the PDB file. And the residue consists of a list of atoms. Okay, the ordering matters in this file, and a list of bonds. Now the atom names are actually not used as well, but because the PDB file has atom names, it's good to set them the same to avoid confusion. But there is something called the atom type, which is going to become really important soon. The atom type, you see, because the formaldehyde residue, I've decided to call it FML. The atom types, I use FML dash followed by the name of the chemical element. That's just the choice that I made. You can really use any name you want for the atom types, although it's best to be systematic. And the atom type doesn't actually show up in the PDB file. Okay. Finally, you specify a list of bonds where the bonds go from where every bond connects two atoms, and that's why the ordering of the atoms matters. Because if I order the atoms wrong, then the bonds will be wrong. Okay, but and now let's look at the next section. This specifies the atom types, and in force fields, there's always a bit of a bureaucracy when it comes to how to categorize atoms. And in OpenMM, the first thing to know is that the atom type is the most specific way you can categorize an atom. Okay, and an atom type completely specifies all the physical interactions that atom could possibly experience. Okay, but there are coarser classifications that are available. So every atom type can be further assigned to an atom class, and atom classes are just more convenient methods for you to describe the interactions between atoms in a more compact way. So say if you have a whole lot of atom types that have the same van der Waals interactions, you can describe the van der Waals interactions using an atom class instead of an atom type. So atom classes are mainly just a convenience, but there's also this attribute that specifies the chemical element. And the chemical element is important if you want a custom molecule to be in your simulation, because that's going to go into the PDB recognition. Okay, so the element matters mainly for recognizing the PDB file and matching it to the template. And you see, because every atom type is mapped to an element, we actually know which we actually know the atom class and element of every one of these atoms, right? Because of this mapping. Okay, then we can start to talk about the physical interactions. And in this case, the non-bonded forces are given in terms of atom types, whereas the bonded interactions, like the harmonic bond force and harmonic angle force, are given in terms of their atom classes. In this case, it doesn't actually make any difference because there are 3 atom types and 3 atom classes. Okay, but in a more complicated force field, you can imagine that there could be 10 atom types and only 4 atom classes, but not the other way around, right? There's always, atom types is always the most specific, and it's also going to be the most numerous. And where it says non-bonded force, there are 3 parameters that determine the non-bonded force. This is really the standard Amber form non-bonded force, which involves a pairwise Coulomb term describing electrostatics, and a Lennard-Jones term describing the dispersion interaction at long distances and the repulsive interaction at short distances. And the three important parameters are the atomic charges. So I've given carbon a charge of plus 0.45, oxygen a charge of minus 0.45, and then the sigma and epsilon parameters that describe the Lennard-Jones interaction. Okay, and then the harmonic bond force and harmonic angle force are somewhat self-explanatory because each attribute has a name. You see, the length parameter tells you the length of the bond, and what is the native OpenMM unit system again? What unit should the bond length be in? Nanometers. Okay, perfect. Yeah. So you see, and so you see 0.12 nanometers is like 1.2 angstroms. That's a reasonable length for a carbon-oxygen double bond. Yeah.
Yeah. Just a quick question for the non-bonded forces. How are the charges determined? Because I would think that it would vary depending on if it's carbon attached to oxygen or something else. Are those combined depending on what is attached?
Yeah, that's a good question. I could have planted that question. So the charges can be determined many ways, and there is no single unambiguous way to do it best. The way general force fields typically do it, like GAF, okay, is to calculate the electrostatic potential of the molecule in some geometry using a quantum method, and then fit the partial charges to that. so that the electrostatic potential at some distance from the molecule on a grid is matched. Okay. Now OPLS, which is where I've borrowed the parameters from, does it a little bit differently. There, the charges and the Lennard-Jones parameters are both parameterized to give you the correct density and solvation-free energy and maybe some other condensed phase properties of a collection of organic liquids. But they're chosen in a special way so that if you combine the atom types together to make your molecule, the charges will be neutral within a very small region of the molecule. And in that way, the force field is modular, and you're able to build up a larger molecule. So that's how OPLS does it. Okay, so something that might be going through your mind right now is that this is a lot of text to just go through for a small molecule like formaldehyde. If I had a buckyball or something, and well, maybe a buckyball wouldn't be so bad, but if I had I don't know, if I had Taxol or some other ligand, I couldn't be expected to just type this, right? So this is something that could be in a very it could be in a very new. This would be in a very near future release of OpenMM, where I've written a script to automatically generate this from the Amber force field files. So by this I don't mean parm top or in chord, but you can generate this XML file from the human readable Amber files that are one step up. So I'm working on these scripts, and I'll be working with Peter to put that into a near future release of OpenMM. Another alternate way for you to do it is to set up your system entirely in Amber, okay, and then just import the coordinates and parm-top file that come out of that. But it's important to know that once you've that the parm-top and impcord files from Amber are not editable. They're kind of pre-digested. If you read them, they're just kind of like a sea of numbers, right? But this is one. But a script to convert from the Amber force field file to this would be a way for you to become more familiar with the OpenMM format and get to use the modeling tools more and so on. Okay, any questions about this? Yeah.
Yeah, it strikes me that what seems challenging to me is mostly figuring out the topology for a new molecule. That in many cases you might have a force field that is probably going to be adequate, but like you said, for something like Taxol, just having to put all the bonds, the angles, the dihedrals, are there tools that can automate that for a new molecule, or like is the current state of things that you have to go through one at a time?
Right, we would never expect you to have to do that by hand for any molecule. So the scripts can handle that by recursively walking through the bonds. You can figure out what molecules are bonded if you have a reasonable starting geometry just by using the interatomic distances and covalent radii, and then so you can determine where the bonds are. And once you determine what the bonds are, you can figure out what the appropriate angles and dihedral interactions should be, and then depending on what and depending on what interactions you have, then the parameters will come out of some general force field. So that's so actually the Amber modeling tools does all of that for you, and the script that I've written that hasn't been released yet will take those files and convert it to this. So you wouldn't have to specify the topology by hand. There's other challenges involved, but that's actually not one of them. Sure. Okay. Well, let's talk about the next section now. So the point that I really like you guys to take home is that you need both the force field XML file and the topology from the PDB in order to create your system, right? I mean that's in the for the specific pathway that I'm talking about. Like there's other ways to create your simulation object, but a force field file by itself is not enough. You also need the topology from the PDB. So here's a really simple PDB file that I've actually just taken out of the exercise, where you have 7 atoms. The first 4 atoms belong to the formaldehyde molecule, and the last 3 atoms belong to the water molecule. The PDB specification is actually hundreds of pages, and I think we're only using a small part of what the PDB can do, the PDB format can do. But as you can see, each residue has a name and a number, and there's also the atom names. Okay, so if you're building a custom molecule, the residue name and the atom names actually don't matter. Remember that the force field XML file also has residue names and atom names, but the matching is only done based on the chemical elements and the way they're connected. And because of that, you can actually specify your atoms out of order here. Although, in order to avoid confusion, it's probably best to keep them in order. The chemical element is specified on the right column here. This is not always present in PDB files. Okay, so if you want to set up a custom molecule, you should make sure that the element is there. I'm also giving you all this information, so in case you want to write your own script to do this, it's not that horrendously difficult. And then here, oh yeah, here are your here are your atomic coordinates. You see this column is all zeros because our system is so simple, all the atoms are actually in a plane here. And finally, the HET ATM stands for heteroatom. That's for that's just to that's the record that specifies any atom that is not part of an amino acid, essentially. And then connect, misspelled, but that specifies which that specifies how the atoms are bonded. So where this says 1, 2, 3, 4, that really just means that that atom number 1, which is carbon, is bonded to atoms number 2, 3, and 4. And so OpenMM does read the connect records when working with custom molecules. So that kind of gives you an idea of how it works. A final thing that I kind of figured out by trial and error is that even though the residue name doesn't strictly matter when you're setting up your system, if both of these columns had the same name and number, the recognition wouldn't work. Okay, so the combination of the residue name and the residue number should be distinct for different residues. Otherwise, it would be recognized as a single one, which hopefully makes sense. Okay, so here I've given you a bunch of commands. You don't actually need to type this in. It's just kind of to give you an idea of what you could type in if you wanted to learn about the names of your atoms and bonds in your system after you've loaded the PDB. So you see, after I've loaded the PDB file on the first line, the PDB object contains a topology object. That's the second line. So I've created a new variable where I've extracted the topology object that's inside the PDB object. And the topology object contains a list of atoms and a list of bonds, which I've gotten on the third and fourth line, and I can print them out. So that's what's used to create the system. And once I have the topology object and a force field object, I can create the system, which is on the bottom line here. Okay, and finally, if you've set up a system that you want to reproduce exactly in another script, or if you have a system that you want to use over and over again, like over a long time, and not have to worry about setting it up every time, you can save the entire system object to disk using something called the serializer. This is a slightly more advanced usage, I would say. But if you use the XML serializer class, which is automatically imported into your Python script when you load the OpenMM libraries, it will turn your system object, remember, which specifies all the particles in your system and all their physical interactions, into a string. Now the string is actually can be written to an XML file. It's valid XML, but it's different from a force field XML. Okay, because the system XML is much longer. Because it specifies all the particles in your system, not just the number of residue templates. And once you have the serialized XML, you can write it to disk, and it can be read back in. So that's so in the class diagram, that's another way to set up your system. Okay. So now I'm not sure how much time is left for the exercise, but the scenario I've created is that suppose there's a part of your research project, but you're actually continuing a research project that a senior grad student started, but they've now left the group and they left it incomplete. There's no documentation, so it's confusing, and they're not replying to your emails. Like, this happens a lot, right? So basically, the residue section of the force field XML file that is provided in the exercise is incomplete. Okay, but based on your knowledge of the XML file, which I've given you, you should now fill it in. It's only a couple of lines. It's not daunting, and then you can execute. Then you can execute the script that does the energy scan. Now the script that does the energy scan has a fair bit of Python scripting in it, so you can read it to learn a little bit about Python, but you're not actually required to know precisely what's going on in the script. Although it does kind of demonstrate like the flexibility that you can achieve with OpenMM, right? And then once you get the results, you can plot the resulting energy profile and see if you get something that looks like the literature. I've actually provided a file called mp2.txt, which contains all the energies from the high-level quantum method. So you can compare OPLS to the quantum method, although the amoeba part is not a part of this exercise. And then finally, something you could do for fun if you have time is you could tweak the force field parameters by hand, especially the non-bonded parameters, because they are what come into play for this exercise, and see if you can reproduce this MP2 result a little bit better than the original OPLSA parameters can do. Okay, so that's it for this presentation. If you want to learn a little bit more about how to optimize force field parameters and also how to gain some flexibility in extracting data from your OpenMM simulation, I'll be giving the Track 1 workshop this afternoon. Thanks.